Alright, so we are going to be talking about our calculation for today. Last time we talked about heat and what heat is. Today we're going to see how we put that together, usually in a thing called calorimetry. So you want to get out your notes, take a little bit of notes, but this notes are going to have the sample for how to do your lab today. So calorimetry, which is basically what we are doing today, and pretty much what we do in all our lab. We do a form of calorimetry. And calorimetry is that process to find the energy in an object. Now today we are actually going to use that process to help us find the specific heat capacity of an unknown metal and use that specific heat to identify that unknown metal. Now it works by conservation of energy. Conservation of energy, because and we have our calorimetry, we have a number of things. Now today we're going to have two things. We're going to have some water, we're going to have some metal. Might have more things, like when you do food, how do they find food calories? They have things called bomb calorimeters. Basically they burn it. Like we're going to do a lab where you're going to burn some food and see how much energy is in it. But they put in a bomb calorimeter. Other types of things like the experiment we do today would basically, if you are a materials engineer, this is one of the things you might do, because when you develop a new alloy, a new metal alloy or a new substance, I mean, you have to figure out what's its melting point, what's its boiling point, how much energy to melt it, specific heat capacities. There's a whole bunch of constants you have to do. So you'd have to do an experiment like this to find its specific heat, at least in its solid state, because we're going to be dealing with solid metals. By the way, in lab today, each group has different metal. So if your numbers aren't coming out like your neighbor's numbers, that's okay, because they have a different metal. And I can get metal any color. Metal, these days in material science, do you think when you buy something and it's like in a green aluminum box, do you think aluminum comes out green out of the ground? It's kind of like, do you think metal has this color? No, it's something they add to the metal. It doesn't really change a lot, but it gives it color. So metal can come in any color it wants to on that. But the idea here is no net change. No net change. Something's going to gain, something's going to lose. But whatever something loses, something else gains. And they'll always end up at equilibrium, which means the final temperature for all the objects involved is always the same. The final temperature is always the same, which means if we have some things, some gain energy, some lose energy, but the sum is going to be zero because it's going to be identical. Conservation, we're not going to lose anything. In other words, we have an MC delta T term here where it's going to have a positive, plus an MC delta T term here where it's a negative, and it's going to equal 0. Now in our lab today, we only have 2 items we're going to have to worry about. Sometimes you might have 3, 4, 10 items so in our calorimetry, but today we're only going to have 2. Really, the only thing we're going to worry about is our metal and some water in the cup. We're not going to really worry about the cup. The cup's styrofoam. The amount of energy it loses and gains is negligible, especially with the equipment we have. It's going to be negligible. But how do I calculate that out? Anybody need more time? We have this problem. Now, basically, all the numbers, you need to write down this problem. All the numbers given in this problem are the numbers are basically the values you are going to measure or calculate in lab. There is one calculation because you have to find out how much water. Because you're going to mass, basically you have a cup, and then you're going to put some water in the cup, so you're going to have a mass of water in a cup, and then you have to take away the cup. So you need to get the mass of water. But all the numbers that you have up here, you're going to get in your lab. You're going to be taking measurements and getting those numbers. The only thing that you're going to have at the end is to find the specific heat of the metal. Now, mathematically, you're going to start seeing letters and numbers, and sometimes people get very nervous and they freak out because there's too many letters. In the grand scheme of things, that's the problem we're doing. In algebra, This is the algebra problem we're doing. 3 plus 5x equals 0. Can you guys do 3 plus 5x equals 0? Have you done 3 plus 5x equals 0? Now, granted, our numbers are going to be like 80,000 plus 300x equals 0. But still, it's still just 3 plus 5x equals 0. So don't let it freak you out. All right? In all these letters that I'm going to put down, there is only one you do not know. And that is the specific heat of the metal. One. One out of all these letters you don't know. Everything else will be there for you. So let's write down what some of these things are. So we have metal, and we have water. So our problem says a 5.5 kilogram sample of an unknown metal at 55 degrees Celsius is placed in 1.5 kilograms of water at 15 degrees Celsius. They reach equilibrium at 25 degrees Celsius. What is the specific heat of the unknown metal? So first of all, we have our metal. What is the mass of the metal? 5.5 kilograms. Mass of the water is 1.5 kilograms. The start temp of our metal is 55 degrees. Yes, 55 degrees Celsius. The starting temperature of the water is 15 degrees Celsius. And so we're going to put the metal into the water, and the metal is going to lose energy to the water until they both reach a final temperature of 25 degrees Celsius. They reach a final temperature. Remember, when they reach equilibrium, everything has the same temperature. We're trying to find the specific heat of the metal. Metal. T start. Well, this has its starting temperature. This one has its starting temperature. When you put them together, they're going to end up at a final temperature. They're both going to, that's what, when we reach equilibrium. That's the thing about caliorimetry. They all reach the same temperature. In our lab today, the metal and the water will reach the same final temperature. Yes, ma'am.
What does it say? It says find
C of metal. Now, we do know one thing. Now, one thing is a constant. We know C of our water is 4,187 joules per kilogram degrees Celsius. That is the C for water. We know that. That's a constant. You know, that's a fundamental constant of water. And in your lab, you know what the specific heat of water is. Which means whatever heat the water gains plus whatever the metal loses, can't spell metal today, is equal to 0. Remember, I'm going to take a cup. I'm going to put the metal, this hot metal, into the cup of water. The metal's going to lose energy to the water till they reach equilibrium. But whatever energy the water is gaining, the metal is losing. This is what calorimetry is all about. So mass of the water, C of the water, T final minus T start of the water, plus mass of the metal, C of the metal, T final minus T start of the metal, all equals 0. Now, this is about the time people start getting nervous. They see all those letters. But remember, do we know what the mass of the water is? You know, we do. Do we know what C of water is? Do we know what the final temperature of the water is? Yeah. Do we know what the start temperature of the water is? Do we know the mass of the metal? Do we know the final temperature of the metal? And do we know the start temperature of the metal? The only thing we don't know is C, which is what we're trying to find. But everything else there, I have a number for. Do we like numbers? Do we like numbers better than letters? So I just put my numbers in. So I have mass of the metal, 1.5, or mass of the water rather, 1.5 kilograms. C, 4187 joules per kilogram degrees Celsius. 25 minus 15 degrees Celsius plus 5.5 kilograms times C of the metal times 25 minus 55 degrees Celsius all equals 0. You guys a chance to catch that up. So now I have a number plus a number times a variable equals 0. Now we're kind of at that 5 equals 3x equals 0 stage, or 5 plus 3x equals 0 stage. Well, those are all the numbers from the problem. Remember, those are all the problems. These are all the numbers I wrote from up here, right? My problem, right? Mass of the metal, T of the metal. You know, these are the numbers that we're given the problem. These are the numbers you're going to have in your lab, that you're going to measure in the lab. They're going to be in your data tables. All right. So when I multiply this out, now with joules, we tend to get larger numbers. Now your masses are going to be like 0.1 kilograms of water and 0.0 something kilograms of metal, and so you're going to have smaller numbers, but they're along these lines. Whenever we use joules, we start getting thousands of joules of energy, or kilograms, and things like that. So I have 1.5 times 4187 times, now right here, that was 10 degrees C. This one will be negative 30 degrees C, right? That's the difference. Times 10. And so I get 6,200 or 62,805 something. Well, let's look. Kilograms cancel, degrees C cancel. I am with joules. So that one is joules. 62,805 joules of energy. Plus, well, here I have kilograms times centimeters squared. So I have 5.5 times 30. And so I get a negative 165 kilograms degrees C times C in my metal, and that equals 0. So notice, now we really are, remember? Number plus a number variable equals 0. So we're really at that, 5 plus 3x equals 0 thing. Anyone not see where I've gone at this point? So all I have to do, I'm going to subtract 62,000 something from both sides. I end up with negative 165 kilograms degrees C times the specific heat, negative 62,805 joules. I divide both sides. Now it's just a plain old algebra problem. Now I want you to look. Joules per kilogram degrees Celsius. Is that the unit of specific heat? No. It is. Joules per kilogram is the unit. So, okay, so far I'm on track. Negative divided by negative is a positive. Specific heat is always a positive value. By the way, if you end up with a negative value over here, you should be thinking, okay, I might have done something wrong somewhere. And go back and look, because you should end up with a positive. And when I divide 62,805 by 165, I get a specific heat of the metal of 380.6 joules per kilogram degrees Celsius. And if you look at that chart, look at your procedure sheet. On the back side is a chart of different metals. What metal is this specific heat close to? Copper. So in my lab, if this is the value I got for my final average, I would say, well, this has a good chance of being copper. It's close to zinc. Then you have to make a decision of which do you think is closer. Yeah, I know it comes out. The zinc is what, 388? 385? Well, then you might say it's